Hello, everybody. It's 2 o'clock, so I will get started here. Thank you for joining the Committee on Geological and Geotechnical Engineering, COGGE, for part 2 of our webinar series regarding the February 2017 incident at the Oroville Dam. My name is Samantha Magsino. I direct COGGE alongside our committee chair, Marty McCann, who is also on the line. We are excited to welcome our guest speaker, Stephen Rigby, a member of the team of technical experts convened to conduct a forensic analysis of the Oroville Dam incident. He will discuss the lessons learned from the incident and their effects on dam safety practice. And for those of you who joined us last week, we heard from the chair of that committee, John France, about the physical aspects of the failure. The webinar will include a Q&A session following Stephen's presentation. Please send your questions to me in a private chat within Zoom. I will read them out for Stephen as time permits. Please do not send them to me via email because I have this presentation on my screen right now and I'm not monitoring email. Let's see. Figure out how to move forward. There we go. As we did last week, I'll provide a quick overview of COGGE. We are a standing committee within the National Academies of Sciences, Engineering, and Medicine that serves as a focal point for government, industry, and academia for consideration of the technical and public policy issues associated with the engineering applications of the earth sciences. So we look at the mechanics and processes of earth materials, both soil and rock, and how we safely and responsibly engineer within them. Our job is to identify issues worthy of attention by the National Academies so that our stakeholders in the private and public sectors and in academia will be more informed as they go about their jobs. COGGE's twice-yearly meetings often include open sessions during which we invite the technical community to engage on a variety of topics. We also host informational webinars like this one on topics about which we'd like to learn more. COGGE members are nominated by their peers. This is a list of the current committee members. They're nominated by their peers and Academy staff based on their expertise. COGGE, as I mentioned, is currently chaired by Marty McCann, and current membership reflects the range of issues about which we're interested. We're currently waiting approval for 4 new members, and we expect it any day. Unfortunately, I can't share those names with you until they are approved. So here you can see a snapshot of some of our recent report covers. And these are all studies that were conducted under COGGE's purview. The most recent of which is about making decisions for managing surface water flow and sedimentation rates near Mount St. Helens. Many of you may be familiar with a report we released last year on earthquake-induced soil liquefaction and on a report released a little while back on dam and levee safety. As you might be able to tell by all of these titles, many of our reports are multidisciplinary in nature. And along those same lines, we have a multidisciplinary group of sponsors. We've been long recipients of core funding from the National Science Foundation, the Mining Health and Safety Research Office at NIOSH, and the U.S. Nuclear Regulatory Commission. And in the last few years, we've received core or study support from, among others, Federal Highways, DOE, NASA, the Bureau of Reclamation, the Forest Service, the Port of Los Angeles, the Port of Long Beach, the Geo Institute at ASCE provided some funds for a recent work, so Los Angeles Department of Water and Power and Geosyntec. And you can see this list of sponsors that, by this list, that COGGE's mission is of interest in many different sectors. The inception of all of the activities that led to these reports and others that we've done over the years was discussions among COGGE members and staff and our stakeholders. We work with our stakeholders, that would be all of you and more, to determine what questions could be answered by the National Academies. COGGE may only have a few members at a time, but we're always looking for ways to increase interaction with the technical community that we serve. We want you to be a part of our conversation so that we can learn about the topics we should be pursuing. So we hope that you will participate in our roundtable discussions, either in person or remotely. Our next meeting, by the way, is March 26th. You can join us remotely for that. You can also join us for future informational sessions like this one that we're having today. If you already aren't on my mailing list, go ahead and pop me an email and I'll make sure that I sign you up. Again, let me remind you that we'll wait till after Stephen's presentation for question and answers. If you have a question for Stephen, please use Zoom to send it to me via private chat. I'll read your questions as they seem most related to the discussion at hand, and as time permits, please forward further questions about the forensics report to Stephen Ruby, and we'll provide you his email at the end. Let's see. And before I hand the microphone over to Marty to introduce our speaker, I'd like to remind you that this webinar is informational only, and that the independent conclusions and recommendations that are presented by our speaker do not represent recommendations of the National Academy of Sciences, Engineering, and Medicine. And with that, I'll hand the microphone over to Marty, and he can introduce our speaker. And I really hope you enjoy this webinar, which I think is going to be really informative. Marty?
Thank you, Sam. And glad everyone could join today. As Sam mentioned, John France, who was the chairman of the forensics panel, sort of walked us through the physical aspects of the Oroville incident. What seems to be equally important and may have greater implications, if you will, with regard to not only Oroville and DWR's future management of it, but also the lessons from this event to the broader issue of dam safety, in that the elements of this event, which go beyond the physical, tell us or has told us things about dam safety practices and how we go about our business in dam safety. And the forensics team has commented on that, on those types of issues. And so Stephen is going to speak to the broader lessons that the panels spoke to in their report. Stephen is currently the Director of Dam Safety at BC Hydro in British Columbia, Canada. And he's been in that job for the last 10 years. Prior to that, he's been a consultant in the dam engineering, dam safety area. And throughout his career, he has been active in the Canadian Dam Association and also in ICOLD, the International Commission on Large Dams. So he has considerable depth and breadth of experience and served a unique role on the forensics panel. So with that, Stephen, thank you for agreeing to participate and share the lessons from the panel's work, and I'll turn it over to you.
Thanks so much, Marty, and thanks for having me here. It's nice to be able to share this presentation with this audience. I'd like to start by putting our work in a bit of context. We had to literally sift through hundreds of documents, and we went through about 75 interviews. And even after all that, what we found is that we were still missing a fair amount of information, and we also had a lot of conflicting information. So what I'm going to present is really our best interpretation of what actually happened. And this is particularly in the context of the decisions made during the incident. So with that brief introduction, I'm going to dive right into the summary of our findings. I'm going to essentially walk us through the executive summary of the report. And as you learned last week, the physical aspects were fairly easy to discern. It was water injection through cracks and joints in the chute slab, uplifting a portion of a slab or a small portion of a previous repair. Once that uplift occurred, there was very quickly a large amount of erosion of the very poor quality foundation rock by the high velocity water. The problem was, once that had happened, there were a lot of very, very difficult risk trade-offs that had to happen between using the damaged spillway and the potential use of the emergency spillway, which had actually never been used. The decisions that were made, which I'll go through in a bit of detail, resulted in the emergency spillway being used, with subsequent downstream erosion and the necessity for the evacuation order. we never found one root cause or one single path to failure. It was really a long-term systemic failure of just about every industry practice, regulatory practice, and internal DWR practice of dam safety that were all intertwined to cause the incident to occur. None of them recognized or addressed the inherent design construction weaknesses, the poor bedrock quality, or the deteriorated spillway chute conditions. The big lesson is that this happened to the owner of the tallest dam, not regulated by one, but regulated by two agencies, repeatedly evaluated by very reputable people, and it's a wake-up call for everyone in the dam safety industry. What we have to do now is check and challenge our current assumptions on what constitutes, or what we believe constitutes, best practice in our industry. It's long, long overdue. So we put together this diagram, which looks a bit complicated, but it was an attempt to show how the physical factors and human organizational and industry factors intertwined to make this incident occur. The physical factors are in blue, the human organizational factors are in the flesh color, and I'm going to work down the timeline through the middle of this diagram, starting with the initial design concepts, the final design, and how that led to the initial cracking and the high drain flows. So, as you heard last week, there was initial cracking that occurred literally a month after the spillway had finished construction. You can see them there in the diagram here. They essentially were tracing the outline of the underlying drainage system. This led to a path for water injection, and there was, again, right from the very beginning, large drain flows. You can see all of these drains along the side of the spillway that were collecting the under drain flows and exiting during the flow. That was first noticed in 1969. So these were unrecognized, inherently weak designs. And as John went through last week, there was quite a number of different reasons. There were no water stops or anything between the open joints in the concrete slab. The concrete slab itself was only designed to be 18 inches thick, and within that 18 inches, the under drains are actually protruded into that thickness, so that the end result over here is that you had, in some cases, only 8 or 9 inches of concrete. In there were a series of mat of rebar, of reinforcing steel, which, because the water could get in there, corroded, expanded, popped out these areas of weak concrete on top of it. They were subsequently repaired, and they again failed, and there was a repetition of this patching on top of all of these cracks. And you can see here's where the drain used to be in this piece of slab that was taken out during the forensics. And because of the positioning of the drain, you had this natural tendency for the concrete to crack on top of it. So why? Why were these issues not recognized? There was a total incompatibility of the as-constructed spillway with its both foundation and hydraulic conditions. Well, we did know at the end that there was an inexperienced designer involved who had very little oversight. But the main thing was there was the lack of adjustments as the in situ conditions became apparent during construction. This lack of adjustment was mainly due to a poor communication. There was DWR, as many owners were really siloed into design, build, and operate divisions, and that was one major issue. So back to our diagram. What did all this cause? with all this cracking in the high drain flows? Well, there was a whole series of things going on. And there was, again, no one path to failure. There was certainly some ongoing cracking and spalling, that the water flows under the slab were causing a little bit of erosion to occur, not much, but a little bit. There was through the years, a loss of drain capacity. The repairs kept failing. The anchorage of this spillway slab, as John would have told you last week, was beginning to corrode. And of course, the reinforcing steel itself was corroding as well. So all of these things were happening at once. The thing was, along with the repeated ineffective repairs, which is a physical factor, there was a normalization of deviance. People saw this, but because it had always been that way, they never recognized it as being a real problem. I'll give you some examples. Back to the picture of the cracks above the drains. These cracks in 1969 were noted. It was very clear that they were on top of the under drains, and it was stated in a report from 1969 that an inquiry to the designers regarding this aspect would be in order. However, we found that that inquiry was actually never made. We certainly couldn't find any evidence that they ever actually got back to the designers about this. They called the high flows mystifying, but probably not dangerous. Now, 10 years later, 1979, they're now referred to as frequent but probably unimportant cracks. Flash forward to 2010, and the corporate knowledge of why those cracks are there and what their significance are has actually been lost. The repaired herringbone crack pattern is said to reflect the underlying drain system. Things just became normalized over time. Again, with the flows, same thing. The same inspector that wrote in his report in 1969 that these flows were mystifying and had to be investigated and discussed with the designer by 1973. The same guy is writing in his reports, all conditions are normal. Outside consultants also perpetrated the problem by essentially noting that there was no formal monitoring program for the flows, but they never asked for any. Back to our timeline. So we had all of these things going on underneath the slab and being considered to be normal. But there was still this whole issue about the unrecognized poor foundation conditions. And how did that happen? Well, the specifications for this project were quite normal. It was essentially clean out, poor quality rock, down to a solid rock foundation. As you can see in this picture near the top of the spillway, you can see the nice, good, solid pieces of rock, which were then cleaned by jets of water and air. And the same thing, as they started to move down the spillway chute, you can see the same thing here. Now, there's a guy standing, so that's got to be up to 6 feet of excavation to get down to this good rock. And you can see these sonotubes here to extend the drains down to the foundation surface, indicating that the drain system was designed to pick up any water inflow into the drains from the foundation. They were not designed to pick up water getting in from the surface down. The problem was there was a major claim during the contract because the contractor was making out like a bandit. He was excavating all of this material, backfilling it all with concrete, and because the specification didn't cover this possibility, it was all on time and materials, and he was making a good buck out of the whole thing. DWR was getting very worried about the costs, and they made the argument that it was the contractor's excavation technique that was causing the problem. And their philosophy was the rock is good. It's your problem that you're excavating so deep. So they ordered the contractor to only go down the 18 inches as per the original design, and they relaxed the specification to allow what they call 50% compacted clayey fines, which was essentially just the broken up weathered rock on the surface to stay in place without any washing. So as the years went by, there was a corporate myth that the rock was good And we believe that started because of the DWR defense against the contractor's claim. However, there were missed opportunities along the way to really check this out. There were two specific studies in 2005 and 2009 to look at the erodibility of this rock when it was questioned whether or not the rock was actually good. These reviews actually appended the details showing that the rock was highly and strongly weathered. However, they concluded the rock was good. But nobody caught this. There was no internal reviews, no QA, QC, no questioning. These were sent to the regulators. The regulator didn't catch the fact that the memos did not correlate to the attachments and the data. All the dots were there, but nobody connected them. What happened after 2005 and 2009, every subsequent study just quoted the 2005 and 2009 reports saying the rock is all good. Back to our decision, back to our timeline again. So we had all of these things happening, unrecognized. The potential for erosion underneath was unrecognized, and we get to the failure of the service slab itself, which looked like this, as you would have seen last week. Interestingly, I'm sure John told you last week that we know a fair amount about the initial failure because there were two guys standing, just happened to be working on a on a communication tower at the point just about 100 feet above where the initial failure occurred. So we actually know a fair amount about the failure itself. But again, it still wouldn't have been a problem or a significant problem had the emergency spillway not been used. So there were specific decisions that were made that allowed that emergency spillway to be engaged for the first time. And there was the subsequent head cutting back towards the overflow weir that caused the necessity for the major evacuation of people. So what happened there? They had to reopen the service spillway after the initial failure, which was about there, simply because the rains were still coming and the reservoir was still rising. There was a whole series of problems to think about and to weigh against each other. First of all, as there was more and more erosion going into the river, you can see the river here has turned brown. There was major blockages beginning to occur downstream. The tailwater level was rising, which was affecting the power plant, and the power plant could have easily been flooded. Had it been flooded, it would have been a major problem, not simply because of the damage to the asset, but the fact that they would then lose one of the major ways of moving water out of the reservoir through the powerhouse itself. Major, major concern. There were other concerns at the same time. As they were continuing to use the service spillway, they were worried about it beginning to head cut back towards this structure. And if that structure, the spillway gate structure, were taken out, that would be a major loss of reservoir containment. You can see here that the erosion was continuing back towards these transmission towers. The transmission towers were the main towers attached to the Hyatt power plant, and thus if they went down, you'd again lose the capacity to move water through the power plant. And finally, they were worried about using the emergency spillway as this water came up behind it because it had never been used. And they now know that certainly down here there was a bad rock. They really didn't know what was going on here. So there was a lot of risks that had to be balanced. And in the end, there were two very strong points of view during the emergency management. And one point of view was to continue to use the service spillway. One was to use the emergency spillway. And the decision makers decided to treat the risks of using either spillway as equal. So they had incoming reports, hydrologic reports, in terms of how much the reservoir was going to rise, and they decided to try for a sweet spot where they'd allow the service spillway to be used just enough so that they'd just get to the top of the emergency spillway without overtopping it. That was the plan. Because that was the plan, they used the mean value from the hydrological models without considering the uncertainty band around that mean. The rest is history. They missed the sweet spot. Overflow Weir did get overflowed at about 3% of its capacity, and it resulted in the evacuation order because there was, as you can see, a lot of head cutting back up to the structure. At this point, it stopped about 10 feet short, and they made exactly the right call to evacuate those people because they didn't know whether it was going to stop there or hit back, and that erosion was going back at a rate of about 10 feet an hour. So the point was that the risks that were being treated as equal were actually not equal. Everybody got the consequences right. Everybody knew that water retention was the big deal. Loss of water retention was intolerable and a paramount concern. Powerhouse flooding was just second because, again, of what I talked about, it would be a very major problem to move the water out of the powerhouse and actually get through the repairs that were going to be necessary if it flooded. Loss of transmission was considered at the time to be a big deal. The decision makers were told at one point that if the transmission tower was lost, they would be out of commission for 6 months. This was actually not true whatsoever. There was a little bit of a problem with people understanding the consequence of loss of transmission. In actual fact, it would have only taken the powerhouse out for a few days. However, the likelihoods of all those consequences, remember, of course, that risk equals consequence times likelihood, is the fact that the likelihoods were changing, but they were not being adjusted in the minds of the decision makers. People were beginning to understand, because they now looked at the geology in detail, that the headworks were in pretty good shape. They were sitting on good rock. Head cutting wasn't really going to happen. The likelihood of that was going down. They understood now that using the emergency spillway was going to be a big deal because they knew that there was bad rock behind the emergency spillway. And they also knew that their tailwater was actually receding. The problem about flooding the powerhouse was actually, the likelihood of that was actually going down constantly throughout the process. However, surface spillway flows were still reduced, trying for this sweet spot because they didn't believe they had to spill as much as they actually had to in the end of the day. So a whole bunch of lessons to learn here. Lesson number 1, dam owners have to start thinking about having a strong top-down dam safety culture. There was no one executive specifically charged with the overall responsibility for dam safety. The decision makers didn't have a good enough grasp on what dam safety actually required. And in actual fact, this is a org chart of DWR, and it's not that different from many other org charts. And you can see here's the chief dam safety engineer, and here's the decision maker. And there's 4 levels of administration between the two of them. This is not atypical of many people. The point is, the direct line of communication just wasn't there. Lesson 2. It's not all just about uncontrolled release of reservoir. In this particular case, there was no loss of water containment, no loss of life. Really a non-catastrophic environmental effect, but they lost control of water, had the big public evacuation. But what that meant for DWR is a world of hurt. They're over $1 billion in costs to fix. They have more than $61 billion in lawsuits. They've had changes of management, they're reorganizing, and there's talk of charges of negligence. It is a bad deal for DWR, and it could have happened to a lot of owners. Lessons 3 and 4, it's not all about physical inspections. You got to think about what the original design construction actually means. You have to do comprehensive reviews of that. And you can't forget about appurtenant structures. Just because this is the tallest dam in the United States doesn't mean that the spillway doesn't count as well. Lesson 5, Don't rely on your regulators. Compliance with simple regulatory requirements is not sufficient to meet any owner's legal and ethical responsibilities. An owner has to be aggressively inquisitive, got to ask those questions, has to proactively investigate things they don't understand, and to do that, a dam safety engineer needs support from the very top of the house. Finally, lesson 6, we have to do a critical review of the processes that we believe are best practice. They let us down. As I said a few weeks ago at another conference, there's only 2 ways to explain Oroville. Either everyone in the dam safety community is incompetent, or the processes that we depend on are simply not good enough. We have to look at best practice and have an evolution of this best practice over time on a continual basis. Leading to my last couple slides, there was, for those of you in the audience who know what a potential failure modes analysis is, there were 3 potential failure modes analyses done for Oroville. The first 2 missed the failure mode that actually occurred. The third identified the failure modes, but dismissed them as saying they were irrelevant, mainly on the value of the testimony that the rock was good and it would not head cut back up and lose the reservoir. Our report identifies 16 weaknesses with the current process with suggested improvements. But in those 16 weaknesses, I believe there are basic limitations because the PFMA was set up as a practical process. You can get through it fairly quickly, but its practicality leads to some basic limitations. It talks about sequences of events, a nice linear sequence, but in actual fact, this was not a linear sequence of events. It was failures of individual components were not thought about what they would mean to the system, to the safety of an overall system. What we need to do is we need to figure out how a system's supposed to work before we can understand how it can actually fail. Whereas we start at the present time just thinking about how things can fail. There are systems analysis tools out there. There's a whole series of them done in other industries and in other countries. We've got to look at these and understand how can we incorporate them in our dam safety thinking. Back to lesson 6. As I said, there's only 2 options to explain Oroville. Personally, I would rather choose the second option. I don't particularly want to consider myself as being totally incompetent, but the people who reviewed Oroville were certainly as good and better than I am. We need to do critical reviews. We've got to look at other industries and look internationally for assistance in how we can improve our dam safety practices. And finally, maybe most importantly, these are lessons to be learned. We haven't learned these lessons. They're going over and over again. Throughout the decades, we have dam safety failures. We are not learning these lessons. It's time to learn them. So, thank you very much. I'll pass it back over to Marty.
Thank you, Stephen. That was excellent. And given us more than just a few things to think about. Let me start off the questions going back to something that you mentioned in the beginning about communication within an organization, design people, on-site people, involved in the construction and so on. That observation has come up before in past failures. One notable is the Teton Dam failure. It sort of brings up a broad question in your mind, given that we have seen these issues pop up before, in one case contributing to an uncontrolled release of the reservoir in the Teton event, and here a major event but not an uncontrolled release. Would you suspect that there are, I'll say, latent issues out there that are yet to be maybe realized in which at least one of the roots of the problem is the lack of communication, coordination during the construction process. Are there literal, failure modes being slowly played out that we will be realizing them in the future?
Marty, I think that's really quite possible. I mean, I'm not that old, and I remember very, very large gaps in communication on construction sites that I've been on. And even though we think we're much better today, I mean, at BC Hydro, where I'm currently working, we have we're organized in terms of design, build, and operate as well. But we believe we're not siloed. We believe we've got that problem licked. The problem was, we got to remember, we didn't have it licked 50 years ago when these older, when most of our hydro was actually built. So we don't need to think about ourselves now. We got to think about what we were like 50 years ago and what could have possibly have been built in to our structures.
Great, thank you.
Thanks, Stephen. I have a question from our audience. Could we have a little background on the types of claims involved in the various lawsuits, the $61 billion value? Also, what might be DWR's responsibilities as a government agency and or their consultants, contractors in defending and or settling these?
Okay.
And have fun with that one.
Yeah, thanks. I'm not going to touch the second question because I'm not a lawyer, nor have I studied this in any great detail. I can give a little bit of background on the claims. The biggest claim out there at the present time was put forth by the state prosecutor, and it was based on a fine of $10 per pound of material dumped into the Feather River illegally. So the whatever number it was, I can't remember exactly, was based off an estimate of the weight of the material that was washed into the Feather River. There are quite a number of smaller claims. That was by far the biggest claim. There were quite a number of other claims out there from various farming groups, etc., dealing with the problem of the material washed into the river. And that's about all I can say.
Stephen, sorry, go ahead, Sam.
Another question. Out of curiosity, how well did the areas where there was more than 18 inches of concrete fare on the spillway before I assume this means before the DWR kicked in that new rule?
Right. They fared very well. In fact, there are places further up that we excavated as part of our forensics that were actually founded on quite similar rock conditions, i.e. they not quite as bad, but they had up to 50% compacted clay fines. There had been a little bit of erosion underneath the slab, but the slab was in some places 5 feet thick, and there was no issue.
Okay, next question. Please ask Stephen if he considered the possibility of, quote, institutional incompetence, end quote, concerning the understanding of risk and failure processes during his leaning away from the idea of individuals being incompetent in respect of dam safety engineering based on sound evidence. That is, the individuals are calibrated with respect to engineering, but is the industry calibrated with respect to failure processes?
That's a good one.
I'm sorry if I butchered that one a little bit.
Well, I'm going to give an answer, and then we'll have to see whether or not it actually got close to answering the actual question the individual had in mind. In some ways, it would be easy. It would have been easy for the forensics team to have thrown a few individuals under the bus and say, it was all 3 or 4 different individuals' issues throughout the decades. But those individuals acted and made decisions in ways because our industry allowed it. So the question is, why? We're not all incompetent. We have to have systems that allows for human fallibility, because it's always going to be with us. And there's human fallibility in understanding failure modes. You know, one thing we said in our report is you don't develop failure modes in a failure modes workshop. If you don't know the failure mode is, if it's not in your head, if you're not a good enough expert coming into that room, you're not going to figure it out during the workshop. And I think that's one of the basic issues with our current processes is we rely on quote unquote engineering judgment, which in my mind isn't actually engineering judgment, but it's our knowledge that we bring into the process. It's not knowledge we develop during the process. And I think that's what we got to start thinking about is there are other industries out there and that think about failures in ways that you can discover failure modes by looking at how individual components fail and how that individual component is part of an overall systemic failure. And that's what we've got to start looking at. I'm not sure if I answered the question or not, though.
Well, perhaps our listener will let us know. Another question here. What do you hope to learn on risk assessment from other industries and, and internationally that is lacking in current practices in dam safety in the U.S.?
Okay. I think I just answered that question. Actually, it's all about understanding systems. It's the systems thinking. And by systems thinking, it's not only the physical systems, it's the inherent control feedback loops, it's accounting for human fallibility, it's how all of these systems work together to make the overall situation safe, or if components of that system fail, how they interact to make the system unsafe. That's what we have to think about rather than simply thinking about linear paths to failure.
Okay, another question. Oh, this is a good one. How big is the problem of dam safety in the U.S.? Could you estimate a dollar target to fix the dams? How does it compare with other infrastructure challenges in the U.S.?
You know what? I'm as a Canadian citizen, I'm going to pass on that one. As saying I am just not in a position to know the situation well enough.
Marty, do you have any questions right now?
Yeah, kind of a broader take on that question, Stephen, and trying to put figures on anything. But it seems that an argument could be made that in dam safety and arguably in some other industries, that we are not valuing our infrastructure well enough such that we pay attention to the broad range of consequences. And you brought this out in your remarks. Dam safety focuses on only uncontrolled release. Here we have an example of no uncontrolled release, no loss of life, but yet significant impact, physical impact, dollar impact to the owner, obviously impacts to the regulators that were involved, and so on. Is there an undervaluing of assets that manifests itself in run things till they break sort of attitude? That's a little oversimplification, but I'd like to get your comment on that, because that plays into, in my mind, the amount of effort in terms of engineering maintenance staff practices that would maybe abate some of these problems before they arise.
I would tend to agree, yes. I mean, we do have a run to failure mentality that's prevalent in North America for hydro. And, it's because you can run them for a long time. I mean, hydro plants are pretty resilient things. You run them, you've made money off of them for 50 years, but you haven't made huge amounts of money off of them. And that's maybe what the problem is. As time goes on, we now have all of these 50, 60-year-old plants. They're aging. That were not again, not making huge profit margins off of them. And so, yeah, people are resistant to pile money back into them at this point. And from an owner's point of view, yeah, let's run them till they break. What a lot of owners are forgetting, though, is that there's a massive responsibility in terms of water management. It's not just building, it's not producing the electrons that count. It's all about the management of water that counts. And that can have massive consequences if it gets out of control. And I think a lot of owners still don't really get what those consequences can actually add up to.
Thank you.
So Stephen, here's another question. Did the investigators look at the original exploration studies where the elevation to the top of the rock was defined? Was there a misconception? Pardon me?
Oh, I'm sorry. Okay, I interrupted you.
Yeah, I'll start again. Did the investigators look at the original exploration studies where the elevation to the top of the rock was defined? Was there a misconception of how competent the rock had to be for the spillway foundation?
Okay, that's a fascinating story. It starts in 1948 with the very first geologist on site without the benefit of one borehole, looking at regional geology and stepping out of his Jeep and looking across where the eventual spillway would be built. And he wrote in his notes, if a spillway is going to be built on this hillside, there are going to be real issues due to the great depth of weathering. What will have to occur is that there will be the necessity of building a very deep cutoff to fresh rock. 1948, no boreholes. He got it spot on, and that's exactly what Kiewit is building right now as we talk. Okay, flash forward 1962. There's a concept design where they now have some boreholes showing up to 76 feet of strongly weathered rock, and deep excavation for the spillway founded on competent rock. Flash forward 1964, more investigations, more detailed rock showing strongly weathered rock still to 76 feet. However, now what they've done is they've modified the profile, the concept profile for the spillway to be founded on moderately weathered rock, not strongly weathered, but what they called moderately weathered rock. So they've raised it up with the concept that the lining, the concrete lining, would protect the moderately weathered rock. The first, I forgot to mention, back in '62, when it was a deep rock foundation, it wasn't concrete lined. So they went from unlined, strong rock foundation to a moderately weathered foundation with a concrete lining. Subsequently, that particular design got split up. It was a single spillway, it got split up into two spillways. So yes, there was great detail in terms of the understanding of how deep that rock was, and the geological descriptions are totally accurate. Totally. They're spot on. The issue becomes that moderately weathered rock could have produced a foundation had it been actually protected from injection water. However, the designers, and the designer told us this, that he believed he was designing a spillway to be founded on solid rock.
I just got another question come in. To me, this is also a lesson for the engineering profession in standing by their specifications during construction, i.e. not yielding to the pressure of what I call the can't we just mentality. That's more of a comment than a question, but do you have any remarks on that?
Oh boy, do I ever agree with that one. Fully agree. It's all about sticking to our guns. The designers had a reason to think a particular way at the time. We can't do that without getting designers totally back involved with it and not being coerced into accepting something because of a schedule problem or a dollar problem, if it's a matter of this kind of importance.
I'll take a director's prerogative here and ask a question myself. How different are practices today? So if we had construction going on today of a new dam, would you expect similar kinds of things to happen, or is a lot of this because of dam safety practices when this one was constructed?
Today, I would expect designers to be involved throughout a construction period, not to be shuffled off into the corner, and left out of the actual construction work. That's more or less the norm now. However, there are a couple of instances I can think of in the last 15 years of my career where on very small jobs where the designer didn't get to site during the actual construction, which is a travesty in my mind. So on a large job in today's world, I would expect it to be much better. But there are always problems that especially on smaller jobs where that may not actually occur.
Stevens, Marty, you've gone through lessons, and findings of the panel. It would seem that these lessons, which not only have to be recognized, learned, they also need to be translated into changes in our practices, both technically, organizationally, et cetera. Did the panel even informally talk about how big of a job is in front of us in terms of the lessons you've identified and where we need to go?
We talked about that informally, and and I think there was a bit of a difference of opinion on the panel. Some sort of shook a weary head and go, "Oh my gosh, how are we going to handle all of this?" And others thought we could tweak some stuff here and really improve the situation significantly. So I think there's a difference of opinion out there. One reason we thought it was beyond our mandate to give solutions. We were just really trying to be a messenger here.
So if I ask you to speculate from your own perspective, are you viewing the job as rather substantive and going to take a while, or is it a matter of tweaking?
Personally, I'm on the more pessimistic side. I believe we need a shakeup. I personally believe this is going to take a lot of real progress in our thinking, and to make a significant difference. The first step is to acknowledge, and I found this in my own camp, acknowledge that these older designs really have to be looked at critically, because something you designed 50 years ago isn't necessarily what you want for the next 50 years coming. It's going to be a huge job.
Another question, let's see, on the basis of your response to the industry institutional competence question, and given that the panel made recommendations to improve the PFMA process, did the question of the possibility of a, quote, fundamental flaw, end quote, in the PFMA methodology arise in the IFT discussions?
Yes, very much so. I believe it would be fair to say the IFT was split in terms of believing the depth of the flaws within the current process. Some members thought a little bit of tweaking will do it. Others thought that there's some fundamental issues in terms of how we approach it that need to be changed. So yeah, the IFT was split on that issue. And
another comment, probably outside the scope of this talk, but any thoughts on the dam itself?
With the hundreds of documents I read, I must admit, I didn't have time to think about the dam. which is a real shame. I would have loved to have gotten into a bit more depth, because reading through the reports, I hit all sorts of interesting stuff about the green spot and other issues about the dam, and I just had to gloss over them and get to the spillway sections. There was just not enough time.
Stephen,
Well,
you
Marty-
mentioned, yeah, Stephen, you mentioned that you've recognized some things within your organization that maybe need some attention. If you had to sort of step back and serve as, call it an advisor to another owner, what would you advise them in terms of what they need to start doing to take advantages of the lessons that you found in the forensics team work?
The very first thing I would say to any owner, based off of what I learned about our organization after Oroville as well, is stop depending on summaries of previous reports. Go back to first principles and have a fresh look at things. Just ignore what people have been reading or have been writing in these repetitive every 5 years or 10-year reports about year structure. Go back to first principles and think.
So as a practical matter, that makes the current process, or the change from the current process, more time consuming and expensive, because that takes effort. Have you made those types of changes?
Yes, we'd actually already started on some of our major dams, where we have gone back to an original construction notes. And for example, on one of our largest embankment dams, we've just completed a 3D GIS model that now incorporates every single piece of knowledge we have about that dam. It was a massive undertaking. Every single fill test during the construction of that dam is in 3D GIS. Everything that we know about that dam, going right back to field notes, is in that model, and we're still finding stuff out about this dam that we didn't know before. But that took us a year and a half worth of effort with the GIS team. It was a huge expenditure to get there.
So is that the template for what you're going to be doing in the future with your other projects?
That's the template I'd like to follow. Now, in reality, I can see us doing that for our larger embankment dams and our larger dams. For all of our dams, I don't think it's just not going to be practicable to do it for all of our dams. We just won't be able to. We won't have the resources.
All righty. Well, thank you. So I think with that, we'll close the webinar. Certainly want to thank Stephen for his time in preparing and participating in the frank answers to some tough questions. So Stephen, thank you.
Thanks. Yeah, thanks,
and
Mike.
thanks everyone for participating and asking questions and contributing to the dialogue. Sam, do you have any closing remarks?
I'd also like to thank Stephen, and thank you, Marty, and also to all of you that joined us for this past hour. Stay tuned. We're going to be having more of these informational webinars, perhaps every few months, just to keep abreast of some of the interesting things that are happening within our technical community. So with that, I guess we can leave the meeting. Have a great afternoon, everybody.